Welcome to our presentation. Our project is about the implementation of molecular surfaces. And in this talk, we want to give you a short overview of what we have done during the summer of HPC internship. First, we are explaining the terminology we are using throughout the talk. When we have a molecule, due to the uncertainty principle in quantum mechanics, we cannot predict the exact location of an electron around an atom. However, what we have given is a certain probability of an electron being present at a specific location, and this probability is called the electron density. Properties of the electron density are that the density is large around atoms and bonds of a molecule. The density drops off exponentially with the distance to atomic centers. So that means that the probability is relatively high to find an electron near an atom, and if we go further apart, the probability decreases more and more. One of the reasons why we are interested in the electron density of a molecule is that it helps in understanding intermolecular interactions and interactions between other molecules. What we are doing in our computation is to compute isosurfaces of the electron density. An isosurface for a given isovalue consists of all points where the electron density equals the given isovalue. And then the electron density is often visualized with the various isosurfaces for different isovalues. In the right we see an example of a molecule, and the blue and red surface are isosurfaces for different isovalues. Our project is based on the implementation which has been evolved during last year's summer of HPC 2020, and this program computes a triangulation that approximates the isosurface for a given isovalue. Below, we see a workflow of the program. The input is a molecule, which is actually a file which contains the coordinates of all atoms. Then the program computes the triangulation of an isosurface. This triangulation is technically just a list of triangles. And then these triangles can be visualized with an external visualization program, which we see on the right. Now we come to new features and improvements which we added this year. One feature is the distinction between different disconnected surfaces, which I explain now. It is possible that the resulting isosurface is not a single closed compound, but consists of several disconnected surfaces. One example is shown here in the red figure. Here you can see several small surfaces in the inside of one large connected outer surface. For most applications, we are not interested in the smaller surfaces, and we want to sort them out automatically. And for doing this, it is necessary that the computer program can distinguish different disconnected surfaces algorithmically. We have implemented an algorithm which is able to do this. The input is the triangulation, and then the algorithm constructs a tree-like data structure. The result consists of several trees, each tree representing one connected surface component.
In the code implemented last year, a structure that you can see in the figure was implemented to calculate the density on the grid points. It performs atom-specific density function calculations by calling the latter density function for each grid point. I carried out optimization studies by profiling this code structure. Geometric center is calculated as the sum of the coordinates by dividing the number of atoms. Summing the element in an array is performed with the GP reduce operation. I made a performance comparison according to a certain atom number. Since the number of atoms varies between 2000 and 10,000, performing this operation on the CPU gives us better performance. The applied optimization metrics can be listed as reduce function calls, increase the usage of register, reduce the number of global memory accesses, increase active verbs, use fastmath for cost operation, change data types from double to float. In the right chart, V5 represents the last year's code. In the sixth version, if statements were eliminated and lookup table was created. With that, speed up about 10% was achieved. In the seventh version, redundant calculations were dropped by assigning them into registers. Speed up about 3 times was achieved. In the eighth version, fastmath was applied for the cost, the power, and exponential function. In addition to the seventh version, speed up about 33% was achieved. In the ninth version, the function calls were removed and gathered them under the compute density at grid point function by assigning constant values to the register. Since more than one global memory is accessed for a value for each index, this value is also assigned to the register. Thus, global memory accesses were reduced. With this change, an additional 50% speed up was achieved compared to the 8th version. In the 10th version, the frequencies of items were determined and the if statements were ordered from the most frequent to the least. With that, an additional 20% performance speedup was achieved compared to the 9th version. In the 11th version, data types were converted from double to float. With that, an additional 30% speedup was achieved compared to the 10th version. Considering all these optimizations, performance improvement was achieved depending on the dataset between 7 times and 13 times. The chart you see on the left side shows how converting the data type from double to float affects the elapsed time for the memory allocation. A performance speedup about from 50 to 200% was achieved for different datasets.